আমি ভিডিওটা আগে দেখো, এটা জাস্ট গত দিনের ভিডিও, যেটা এলাবোরেটিভ ভিডিও ছিল, আজকে একটু কনসাইজ ফরম্যাট।
This section shows how we convert three-phase AC into DC by running it through a 6-pulse rectifier. This is simply 3 sets of full-wave rectifiers joined in parallel. We have used different colours for each wave. Think of them as red phase, blue phase, and yellow phase. You can see this diagram now shows the 3 sets of full-wave rectifiers joined in parallel. We will now run through each pulse in turn. The first pulse conducts the positive side of red phase. The second pulse conducts the negative side of blue phase.
30 degree, 30 degree.
The third pulse conducts the positive side of yellow phase. The fourth pulse conducts the negative side of red phase. The fifth pulse conducts the positive side of blue phase. And the sixth pulse conducts the negative side of yellow phase. This shows the pulses all coming together in sync. It also shows the firing sequence of the valves. Note how in this animation we have introduced the firing angle alpha and commutation process. This explains the concept of how a 6-pulse rectifier converts AC to DC. Although Transpower uses 12-pulse mode, the same principles apply.
Hello. আমরা যেটা দেখলাম সেটা হচ্ছে যে ওই উপরের ইয়েগুলো, এই আবু বকরি, why you are here? বকরি, Abu Bakr, Abdullah. Oh, he is here, and he left the group, and I know that he is going to US. I don't know whether he got the visa or not. Maybe he's continuing again. Anyway, so we see that the top 3 diodes are responsible for the first pulse of the rectifier. The second pulse is coming from the negative, and then third is the top, and the fourth is the negative, is the from the bottom diode, etc., etc. So it is only 2 minutes videos, and I have already sent the link to your WhatsApp. Now today we are going to apply the 3-phase rectifier if there is an LS, that is, if there is a source inductance. Okay. So can you see the book?
Yes, sir.
So now this is the effect of the LS of the current commutation. If you remember, for the single phase rectifier, what we have already done earlier before your midterm, if it is a constant current, and if this is a your D1, this is your D2, this is your D3, and this is your D4. This is your LS and this is your VS. Can you remember this one? Hello?
Yes, sir.
Okay. So if there is LS, then there will be commutation from D1 and D2 to D3 to D4, right? This IS will change its phases. If you remember that, now if I plot this IS, and then this is your GS, and this is your module of the PS, and then so since this is the highly inductive cases, then we have seen that the current, if there is no LS, then we shall get that output voltage will be like this. Can you remember? This is not the place, this is the VC. That means the output voltage here. This is the VT. Can you remember this? Here,
Yes, sir.
Here the D3 and D4 should be conducting, and for this portion D1 and D2, and then again for this portion, D3 and D4, right? Can you remember? And if there is no yellows, then the current will commutating like this. And give him this thing because you always forget. So the wave shape of the current will be like this, and this will be your IT, the capital IT. So all of you should remember these things. Yes or no? Hello?
Yes, sir.
Hello? Okay. Now, if there is a presence of LS, then the shifting of this current will be done like this. So this portion, what is this portion is known as? Where the current will be shifting minus ID to plus ID. What is this U? Omega T equal to U. This portion will be known as what?
Commutation delay.
Yes, commutation delay, right? This is the commutation delay, and then during this process, during this time, all the thyristor will be turned on, then we shall not get any voltage here. Right? Yes or no?
Yes,
And
sir.
we have also
sir.
tried this one. The output voltage will be 0.9 Vs minus 2 omega Ls ID divided by pi. Can you remember this? For the single phase. You forget everything. I am not saying all these things from any book. You have just completed this one in your midterm. So are you familiar with this expression?
Yes, sir.
Okay, good. Now we shall examine these things for the three-phase rectifier. Okay. So next we will include the LS in the AC side and represent the DC side the same as before. Okay. Let me make these things little smaller so that you can see it. Is it visible? Can you see it? এই আমার কি কথা ভেঙে ভেঙে যাচ্ছে না?
না,
Hello?
স্যার।
ঠিক আছে? কিন্তু তোমরা তো রেসপন্স না করলে আমি কেমন করে বুঝবো?
স্যার বই দেখতে
হ্যাঁ,
পাচ্ছি।
স্যার, বই দেখতে পাচ্ছ কিন্তু কথা তো বলতে পারবো না, আমার সঙ্গে সঙ্গে হ্যাঁ স্যার, নো স্যার, না স্যার,
আচ্ছা
জি
স্যার।
স্যার। ওকে, আদারওয়াইজ মনে হচ্ছে যে তোমরা নাই, আমি একা একা বকবক করে যাচ্ছি। এই আবু বকর ইজ দেয়ার, আব্দুল্লাহ?
Sir, I'm here.
Why?
Because
Why?
my microphone is muted, so you give us like 3 seconds to unmute the microphone and just say yes. We are listening.
Okay, okay. Okay,
Yes.
then you have left the group and you have again joined?
Yes, maybe it was the internet problem.
No. From the group you have left.
Which group, sir?
From this 6801-2021.
No, I didn't leave. I'm here.
Oh, you're still here, but
Yes.
eventually maybe you will leave, right? Is there any
Yeah.
news?
I will leave, but I will remain in the group and I will follow the classes, online
Okay,
classes.
good.
Yes.
Good.
Yes, sir.
Good. Okay, then I thought you have left. That is why I am speaking Bangla. Okay.
No,
Okay.
sir, I'm here. Yes.
Okay. So now what we are going to do. We are going to introduce the three-phase rectifier. What we have already discussed in our previous class. And new thing is that we have inserted this LS. Okay, and we have already seen that when the LS was not there, if you remember that there will be pulses, 6 pulses here, 1, 2, 3, 4, 5, 6, and in the video we have seen that. So this one is because of the playing of the this one, and then this second one will be because of the negative, right? So you want me to play the video again? No, I don't think it will. I have already sent the link, you can see. Now the thing is that because of the presence of this LS in the in your AC side, and our DC side is still contain the constant current like the highly inductive load. then how the commutation will be done and what will be the commutation angle and what will be the output voltage that we have to find out, and that will be set in the exam also. Okay, so now if I follow the book here, we will include the LS on the AC side and represent the DC side by the constant current as shown from this figure. Now the current commutation will not be instantaneous, like what we have already seen in the previous video. The current commutation was done immediately, but it is not. It will not be there because of the presence of these inductors, there will be a delay, because these inductors will not allow to shift the current instantaneously from one set of diodes to another. As we will look at only one of the current commutation, because all others are identical. We shall see the shifting of the current from 5 to 1. Okay, is it okay?
Yes, sir. Okay.
So now other thing will be maybe say further, then it will be 3 to some other diodes. So we'll not consider that this one. Now consider the commutation current from the diode 5 to 1 and beginning with the omega t equal to 0 as the arbitrarily chosen. You can choose for your convenience when voltage is higher, then you can start from this origin. Okay, so prior to this, like we are considering the 5 and so say 5 is conducting, and then when the shifting will be, the current will shift from 5 to 6. So before that, the current through this diode will be ID, capital ID, right? And IS will be also capital. This IS will be this capital ID, that is constant current, and you will get suppose the current will go like this. Some other pulses and some phases. So current will be constant, that they want to say. Before the commutation, the current was constant ID, and when the commutation will start, then current will shift, like what we have seen for the single phase rectifier. Current will be like this. It will not go like this. Okay. Okay, then so let us go to see the next figure, 5.35a. That will be clear to you. Okay, let us go to the figure. Little tricky, but not very different. If I make it more smaller, is it visible to you? Is it visible? Can you see it? If you use the mobile, you will not be able to see it. Are you using the mobile? Some of you?
Yes,
Hello?
sir.
Okay, I'll go back. I'll see. Or maybe I can draw the figure here. Okay, let me repeat the figure. So this is one leg and this another leg. The upper figure I am not specially plotting. This is the D1, this is your D3, and this is your D5. That is your D4, this is your D6, and this is your D2. So suppose this is your A, this is your B, C. And is it visible to you or not? I don't know. A, where the A, maybe this is your D, and this is C. This is A, this is your D, and this is. Can you see it? Can you
Yes,
see
sir.
it? Okay. Now, let us go down and see. Nice. Okay. That's good. So here, Mm. Here, we are considering which diet, commutation of which diets. Let us see here. Okay, so from the figure, we have redrawn this one. This is your P point, and this is N point. So, okay, let us see which is the P and which is the N. So this, okay, it is not mentioned here. This is your P point and this is your N point. Okay, so now they're considering the D1 here and also D5 because they will shift the current from D1 to D5 and D6 will be there for the return point. Okay. So now there is this is a circuit that has been repeated. We are only taking the diode number 5 and diode number 1 because the time will be shifting from this 5 to 1 and 6 will be remaining there. Okay. So now during the commutation period, during the commutation period, what will happen? As we have seen in our case of the single phase, so the two diodes should be conducting at the same time. So here, diode 1 and diode 5, and this is your N, like here. So N, so this one will be, they have replaced this one just by this voltage. Okay, and after that there is the inductance LS, and also diode 5 is connected to your C phase. This is your A phase. Diode is connected to your C phase. Suppose here, this is your, so this is your P here, this is your B, C. So this one is connected to diode. This one is connected to diode 1, and this one will be connected to diode 5. And this is your P. So from this P, you will have that this one. And 6 is connected. So if we go back again, the problem is that I can show you the whole thing at the same time. Okay, let us go back here. Here. So what we have done from this N that has been drawn here, this D1, and also this is your from this C phase, and from this one, and also D this one. That has been redrawn over there. Okay. So now look here. Okay, again, this one is the point P. This is your point P and this is your point N. Now, I'm going down. So we have redrawn the figure here, and basically what we are trying to say that the current will be shifted from 5. Prior to the commutation, the full current was flowing from your look at the lower loop, this loop. What is the current here? What is the current? You have to tell me. What is the current? If I make a mesh, IT. So look here. Before the commutation, this diode 5 was carrying the full current ID, right? And now it will be shifted. The current will be slowly shifted from this ID current will be shifted from 5 to 1. So that has been shown in the lower figure. If you see it. Yeah. So okay, here. So diode 5 is carrying which phase current? From the figure, can anyone tell me which phase current?
IC current.
IC current. So okay, commutation start. Here we have taken the 0, omega t equal to 0. before the commutation, what is the current through your diode? 5. Can anyone tell me here from here?
ID.
It is ID. Okay. So after when the commutation will start, how the commutation will start? Of course, if you go remember our these figures, so we will get the highest voltage. And from that one, we will see that the current will flow from 5 to, it will be shifted from 5 to 1. Okay. So if so, before commutation, the diode 5 was carrying the full current ID. So when the commutation will start, this current will going to fall. So this period will be known as the commutation U. And at the same time, if you add these two current, this current will fall and this current will be rising, right? It will be boosted up. This current will fall, it will be increased. This current will be decreased, it will be increased. And here equal. Suppose if the total current is 10 ampere, so here the IC current will be 5 at this point, and IA current will be 5. And so say IA is 8, then it will be 2, then 9, it will be 1, and when it will be 10, and then the commutation is stopped, and the IC, there will be no current through your diode 5, and it will be automatically stopped. You understand it or not?
Yes, sir.
Hello.
Yes, sir.
Okay, now what we have to understand from here, like when the two sets of diodes are conducting, okay, from here you will see that there, when the commutation will be there, so there will be a voltage drop, right? What will be this voltage drop that we will have to find? Okay. Yeah. So suppose this is your VPN, this is VCN, VN, VCN means that one. Suppose this is your from here to here. Oh, the voltage is, sorry, the voltage from here to here. This is your VCN. Okay, this is your VCN, and this is your from here to here. This is your V, right? Okay. So now this is your, they are plotting, this is your VCN, and with the say with the proper phase shifting, this will be your V. So this is the commutation angle. Here the commutation will be occurred. So there will be loss of area this portion. We will have to find out what is this area. Why this area will not be there, we will explain these things. Okay. Remember this figure, and I am now making it say again smaller, otherwise it will not be visible to you. So the current commutation only involves FET A and C, and the commutation voltage responsible is V commutation, that will be VAN minus VCN. Okay, what is this? What is V commutation? V commutation has been shown here, like this will be a V commutation. This will be a V commutation. What is this voltage? This is your V commutation voltage, because these two diodes will be commutated. The commutation will occur between these two diodes, so we have to find out the voltage between this point, and that will be your commutation voltage. V com means that V commutation. Okay. Okay, now so now we have to find out what is what will be the expression of the V commutation. So if we apply the Kirchhoff voltage law, so start from here to here to here, negative positive V commutation, then positive negative minus VAN, then negative positive plus VCN equal to 0. You understand the KVL I have applied here? You understand it? Hello.
Yes, sir.
Okay. So now your V commutation will be then your VAN minus VCN. Am I correct or not?
Yes, sir.
That has been shown here. The V commutation will be minus VN equal to VAN minus VCN. The two mesh currents, here the upper mesh will continue IU, the commutation current, and the lower will be ID that we have already shown here. The problem is that I cannot show you at the same time because we are using the mobile somehow. Look here again. This is your commutation current, the mesh one. This one will be the commutation current. They put IU, and this will be your current ID. Okay. Now, so we have to find out what is IA. What will be your IA? Can anyone tell me what will be our IA here? IA will be IU, right?
IU minus IC.
IA equal to
plus-
IU. No.
IA.
IA will be simply IU. Look here, this is your commutation. This is your IU. But IC will be what? ID minus IU. Am I correct or not? You apply here. Here, IU current is coming here and ID current is going there. So which current is higher? Since IC is positive, so ID minus IU. You understand it or not? Everyone, please.
Yes, sir.
IA will be this current. IA we have already designated this current as IU, and this IC current will be two mesh. You know the mesh. This is the circuit mesh. What is the branch current method, loop current method? Can you remember those? Okay, I am teaching you the first year things. This is your R1. This is your R2. If you have the current like this, then this is your I1 and this is I2. What is the current through it? If it is here, what is this current?
I1 minus I2.
I1 minus I2. See here, similarly here we got the IC equal to ID minus IU. Okay. Hello. People.
Yes, sir.
The master's level, if I have to go like the undergraduate, then this is the problem. Okay, so it is I. Now we want to find out what will be the, these are plotted in figure here, and where IU build up from 0 to ID, and at the end of the commutation, that means omega t equal to U. Okay. What they want to mean is that I, here again I'm writing IU equal to IA equal to IU and IC equal to ID minus I, right? Okay, now this IU that will be building up, but this IU will be built from 0 to this. IU will build from 0 to ID. Okay, at the starting, this IU equal to 0. Then what was your IC? If
ID.
IU equal to ID. And at the end, this IU will be ID. Then what will be your IC?
0.
0. And then what will be your IA?
ID.
ID. That means then this diode will stop conducting at the end of the commutation, and then our circuit will be like this. The current will go like this. You understand it or not? 1 and 6.
Yes, sir.
5 to 6. From 5 to 6, it will go to 1 to 6. You understand? The current was carried by 5, and then at the commutation, and it will shift to 1. So at the end of the commutation, this 5 will stop conducting, and then when all the current will be carried by 1, then this path will not exist. You understand it or not?
Yes,
Yes
sir.
or not? Hello. If you read it, that will be easier for you because I have read it, say 1 hour ago. Okay, now here, what will be your VLA? That means the voltage across your inductance that we have to find out, right? If we apply the Kirchhoff voltage law, then what will be your VLA will be your, since the current will be going this one, then we can write down LS DIA by dt, right? And then we apply the Kirchhoff voltage law. Okay. If we go back, if we apply the Kirchhoff voltage law this way, then negative positive VLA, negative positive VLA, then okay, no drop. Then positive negative minus VLC, that will be your 0. Am I correct or not? No, sorry, not correct. I am not correct at all. Okay, so positive negative VLA, then 1, then negative positive minus VLC, then VCN, right? Positive negative will be VCN, then negative positive, right? Negative positive is what? Minus VAN, right? Am I correct or not?
Yes,
Is
sir.
it okay? Okay, I have done this one and let me check whether I did correct or not. Okay, so here, okay, so first they write down this one. That is not difficult thing because okay. VLA equal to, we have already seen here, the current IA was here and this is your LS. So this is, if this is your VLA, of course that will be your DIA with dt, and IA is already IU, so we can write down this one. This equation is okay, right? Am I correct or not?
Yes, sir.
Hello. Then VLC will be LS DI by DC, and IC has already been there. But since this is a constant, so if you differentiate it, it will be 0, and then it will be minus LS DIU by dt. This equation is also correct. Am I correct or not? Hello. Hello.
Yes, sir. Correct.
Hey, 575. Okay, now we have already written here that they have explained this one. Okay, now applying KVL in the upper loop of this one using the above equation, we want to use the above equation. Then V commutation was, we have already found this, right? VAN minus VCN, right? Hello?
Right, sir.
So then from that point, that if we write down with respect to your what is it? This VAN minus VCN is nothing but the VLA minus VLC. Is it correct?
Yes, sir.
Is it correct statement?
Yes, sir.
How did I do that?
Yes, sir. You proved it.
Also, we have already proved it. And then this VLA we have already found from the figure 5.75. What is that? That is your LS DIU by dt. And this is your minus DLS by dt. So minus a minus a plus. Then what we are getting here, that is your, from here we have getting the LS by DIU bt is nothing but the VAN by VC. This equation is also right. Okay. Hello. And then if we know this one, then we can find out DIU equal to VAN minus VCN. Let's this put here, and then 1 minus LS is there, and then dt, right? This dt is here. Then if you multiply it by omega LS, then that will be your omega t here. Then we will shall integrate these two things and to find out our current, and there will be area. Area under this one will be the AU, whatever we want to find. Okay, let us go and see what will happen. It's very interesting, but little difficult. Okay. Now here, as I have shown here, so we want to now integrate this one. The current is shifting, as we have already told you. The U current, that means IU current will start from 0 and that will reach to ID, right? Yes or no?
Yes.
Okay. And when IU will be your capital ID, then IC will be 0, because IC will be nothing but ID minus IU. So when IU will be ID, then IC will be 0. So we'll integrate this part. And then that will be nothing but, since from here, this one, right? So from this one, and we know that VAN minus VCN is nothing but the VAN minus VCN means the VNC, right? This is my nothing but the VAC. Am I correct or not?
Yes,
sir.
sir.
So, and VAC is nothing but that, okay? CA or AC, it is not a line-to-line voltage. VA is the one phase, C is the another, because it is the line-to-line voltage, okay? Okay, we are forgetting the phase angle, just take the magnitude. So this is nothing but your line-to-line voltage. Okay, so now, if you go there, this VAN minus, and then from this equation number, where is that? This one. We can write down this one, and this is nothing but omega d, and this is the area. This is nothing but the area where what area we have lost. We'll go back to see this one, and if you complete this integration, that will be, this will be integration of sine omega t will be minus cosine omega t. Then if you put them, and then we will get this one. From that one, we will get the expression of commutation angle. You understand it? Hello. Hello.
Yes, sir.
Yes, sir.
Now we will have to find out what is this. That means the line-to-line voltage with respect to this one. That area we will have to loss, right? This is the commutation. This, and again that this will be also the same as your omega ls ID. What is this portion for your three-phase? Let us go back and try to find out what is this. Okay, let us go. So here. Now, from here, it should be very much clear to you that, look here, this is your, if there will be no LS, then our pulse will be like this. But because of the presence of this LS, during this commutation period, we will lose this area. This area will be LSID, and we have already found out from the line-to-line voltage, because if you this is your VCN and this is your say this is your GPN, okay. So, but during this period, this is your VPN. VPN is nothing but VPN will be nothing but that your line-to-line voltage, okay. I can show you VPN is what. Okay, that is good. Let us go back and see what is VPN. Yes. VPN is your line-to-line voltage, maybe from here to here. That means from here to here. When there will not be, after the completion of this phase will not be in the figure, then that will be from here to here. That will be your line-to-line voltage. Okay. So, so we will lose this area, and we have already found this area. What is the value of this area?
So omega ls
ID, right? That will be this area. And from there, we have also found out the commutation angle. What is the commutation angle? Cosine U will be your 1 minus this way. Root 2 VLL 1 minus this equation is very much known. And from here, that will be, instead of writing down your VS, we are using the VLL. Okay. So this is equation 5.82 is very important. That will give. And now we will have to find out what is our will be the average value of your output, right? If the current commutation was instantaneous due to 0 LS, then the voltage VPN will be equal to VN beginning with omega t equal to 0, as in figure 5.3.5. Okay. However, with the finite value of LS during the commutation period, this VPN, now we have to find out what will be. So what it is saying that before the commutation period, okay, before the commutation period, then okay, let us write down. Before the commutation period, oh, where is the pen? Why it is not writing? Okay. Before the commutation period, this part was missing, right? So what they said that then the VPN will be what? What they said? VPN was what? VCN. It will be a VCN. Okay, let us find out why it will be done as a VCN. Why? Sorry. I'm thinking about the. You did not make me. This is your VPN is the small VP small n, right? This is the n, right? Okay. So now, what will be your? Sorry. So what will be your VPN? When what is this current? Tell me, what is this current? What is this current?
Sir, ID.
Okay, so commutation start from here, right? So this phase current was this one, and this one capital I. So what was the drop here? If this is the capital I.
So 0.
0.
0.
If so, then what will be the voltage from here to here? VPN.
So VCN.
VCN. Yes. And but when the current is now not constant, then there will be drop here, right?
Yes, sir.
So then what will be your VPN? What will be your VPN then?
So VCN minus VL. LN else.
Right. That means this drop minus this drop, right? So this drop was not counted when this is constant, but when this is a there is a slope here, then there will be drop here, and that drop has to be deducted, right? You understand it or not? Hello.
Yes, sir.
If you don't understand, then you stop. Sir, we didn't understand. Okay, so what they want to say is that before the commutation, this VPN was here. This VPN was your VCN, but because of the when there is the presence of your what is that, the LS, the current has a slope, and then we'll have to begin. Okay, it mentioned the beginning with omega t equal to 0. However, with the finite LS during this commutation period, the VPN will be VAN minus ds by dut. Why it is like this? Okay, let us see. Apply the Kirchhoff voltage law. Okay. Now VPN. Okay, during the commutation period, if we apply the VPN from here to here, yeah. So what will be your VPN? We are following this one. What will be VPN? Okay. Now this will be okay. Let us start from here. Negative positive VAN, positive negative minus VLA, then positive negative minus VPN equal to 0. You understand? I have gone through this one. This is your VPN. I have gone from here to here, partial voltage law. You understand it or not? Now,
Yes, sir.
VPN will be your VAN minus VLA. And VLA is nothing but the LS DIU by dt. You understand it?
Yes, sir.
Hello?
Sir, why capital N is used?
No, it is this N is taken, okay. This capital N is here. Suppose this is your ID. This one, the P and this point has taken N, okay? You got my point?
Okay, sir. Yes, sir.
This one is the neutral point of your source voltage. And this is the neutral point of your DC side. You understand? This small n the neutral point of your AC side, this capital in the
Okay, it's DC side. Yes, sir.
DC side. Okay. Now is it clear?
Yes, sir.
Okay. Now, so here from there, then we can say that then okay. Yeah. So VPN will be VAN minus VLA. That VLA is this one, and then this VPN is from there. We have already seen that if you take the another loop, that will be your VNN by VCN. Okay, we have already find this one from your 5.78. Okay, let us go to this one and see. 5.7. From the 5.78, we have already seen that this one is the VMN. So we will replace this LSDI by dt by this one. You understand it or not? This one will be replaced by this one. Okay, let us go. VN minus VCN divided by 2. Okay. VN minus VCN divided by 2. Here. So this one from here, this one will be represented by VN minus VCN divided by 2. Okay. Then what will happen? If I put this one VPN, then VAN, then minus VAN by 2 and plus VCN by 2. You understand it or not? And that will be your VAN plus VCN by 2. Okay? You got it or not?
Yes, sir.
This has been replaced by VAN minus VCN by 2. Equation number 571. And then that has come here. Okay. What the LSDI is the drop in the VPN during the commutation interval. The integral of this voltage is nothing but the area, right? We have already seen it. This is, if we integrate it, this is nothing but the area we have already found. Then what is the voltage we have lost? The area lost for the, because we are, that has been taken, this one has been taken what the area was lost here. It was taken for pi by 3. So we have to, this is the area we have lost, and then we have to divide it by the time period, right? Like for the single phase, we have divided it by pi, right? For the full wave rectifier, we have divided by pi. For the half wave rectifier, we have divided by twice pi. Can you remember that? For the single phase one?
Yes, sir.
Hello?
Yes, sir.
So this will be pi by 3. Why the pi by 3 it will be? Okay. So if I set it in your exam, so you should not have any problem to deduce it. Look here. this one. They are thinking like this one. If they start from here, and this will be like this will be like this one like this. So that the positive pulse was 5/3. But if you take this one, that means 6 pulse, that will be 5/6. So we are talking about the 2 phase only. So it will be 5/3. So that we have, with that one we got that voltage loss. Whatever the loss we have got. So we got the area here already, and divided by the time period 5/3. So we have already, this has been already reduced, and you can see that the VD0, that means without LF, that the line to line voltage. I have not probably shown in, but in the book it has been given already. You can see it. If you write down it is with the line to line voltage, that will be 1.35 PL, and that will be the negative portion of this. So that will be your main thing for your, what is that called, if there is a presence of LS. Okay, in a nutshell, then if I say that, what will be the cosine of U? That will be 1 minus, what is that, omega LS ID divided by √2 VLL, right? Can you remember we have deduced it? Hello?
Yes, sir.
Yes, sir.
And this voltage will be, this will be without any LS, and then if there is an LS, then we have to divide it by 5/3. That will be your V. So if I said this one, I will give you the, inshallah, I shall give you the in the exam. If you go back to the previous year's question, I always said this figure. I have given this figure. I normally give you this figure. And with the help of this figure, you have to find out the value of the commutation angle for the 3-phase diode rectifier, also the voltage, total voltage, output voltage for the 3-phase rectifier. I think it should not be any problem now. If you go to through the book, and that will be very easy for you. Okay, so now the next one, we are considering the 3-phase rectifier with constant current, right, as a load. But if you now consider with a constant voltage instead of constant current, then what would it be the case? So this is a 5.6.3. A constant DC voltage side output voltage VD constant voltage. We'll consider the circuit of 5.63, where the assumption is that DC side is a constant DC. DC side is a constant DC. It is an approximation to the figure of 5.30 with a large value of C. Okay, where the 5.30 and where 5.36? Let us see that what is the 5.30. 5.30, right? What is the voltage? Hey, where are you?
Yes, sir. Figure 5.30.
5.3. Oh. Let us see what is the fact. That is the figure 5. This one. Remember this one? Hello? This is the practical 3-phase rectifier. So now we have replaced this one as a constant voltage because we have applied a large value of the capacitor. Then this side will be a constant DC voltage. This one that they told you. Okay. So now 5.36A. What is the 5.36A? Let us see. T4, T5. This one is the 5.36A. Okay. So what we have, they have done. So in that capacitor with a resistive load is being now replaced by a constant voltage source. And suppose they are considering like your say, where is the DN? Okay, this is the DP means that they have make a simple circuit. So that is your AC voltage from here. That AC voltage is nothing but these type of things. We will get that 6 pulse. Okay, that has this is your LS, that has this LS has been here, and this all the diodes will be replaced by the DP. That means the upper side diode, and the DN will be the diodes. All the diodes, the returning part of the current. Okay, returning part of the current that is replaced by here. If so, then we'll get that this one, the VAB, VAC, all these things at what we have already seen here for the constant current source. But here, you will get the same voltage, constant voltage here, ripple type voltage, but we have assumed that we will get a constant voltage here, VD. VD is nothing but the average value of this ripple. Okay, and then what will be the current? Since it is a constant voltage here, so if you follow, oh no, okay, just a minute. Okay, if you look at this figure, so current will go like this. So there will be drop here. This LS and this LS. Can anyone tell me what is this LS and why the double LS is coming now? Hello? Because one LS is from the upper diode and another LS for the return part. Okay. So now since this is like the voltage that is opposing to your thing, so the current will not be continuous, rather than there will be discontinuous current. This is this type of current will get. They have just shown you qualitatively, not the quantitative. And from this one, so okay, what will be the current they will find, and then they will short it the output side, and then they will get the short circuit current 5.87. And all these things you don't need it, but for if anyone wants to do any research in future with this power electronics thing, the main three parameters you have to always find out. One is the displacement power factor, another is the input power factor, another is the total harmonic distortion. And they have plotted it for the displacement power factor. This is your ID by ID short circuit. If this is the expression of the short circuit current, then ID by ID they have plotted by using probably PSpice or PC, any other software. You can always find out this thing. When the ID short circuit is a constant. Short circuit is a constant kind of here. LS omega 1, VLL root 3. I don't know why this is omega 1. No. I have to check on you. You can check later. So then if you plot this one, that means if ID is increased, the load current is increased, then displacement power factor is almost equal, and power factor is now in the low side of the current, the power factor is low, and but in the high current, we see that power factor is almost constant. We have to find out all these parameters if anyone wants to do any research or PhD or masters in future. And they have also found out like the current between the voltage, and they have shown that how the voltage going down, not it is showing the expanded scale. Look here, this is 1.05 and this is 0.95. It is not that much. But we see that with the increase of the current, ID current, the voltage is dropping down. The voltage is VT0 is constant. They have taken the per unit. So it is going down. We have to find out why this is happening. But we can always find out by examining the circuit. But it is not just now, you don't need it. Okay. So the example 5.7 is the three-phase rectifier. Look here for a. Wait, let me show you. This is the three-phase diode rectifier. It's supplying approximately 2.2 kilowatt with VLL line-to-line voltage is this one, LS equal to this one, and CD. That means your capacity, high capacitance, so you can replace this one as a constant voltage. If the load can be represented by the equivalent resistance of the 3.50, obtain the circuit by means of PSPICE simulation. Will you be able to do it? Hello.
Inshallah, sir.
Oh, good. So they have given, or they did not give any coding. You have to do by yourself. Will you be, if you can do it, I can tell you with this program, those who wants to do any research on this type of things, they will be able to do it. You can use the PSIM software or PSPICE software to find out this. I'm not giving you as an assignment because that will be tougher for you. But you have to go and you understand from the previous figure, this kind will be like just falling like 0 and this there. But in the previous case, when the constant kind was there, we have seen the kind was like this, right? Here we get this kind of thing. So this is your VD. VD is not a constant other than there is V people. This is your VBC, this is your VBA, VCA, VCB. The ID current is now IA current. The phase current is like this one, but it is still continuous for this, still continuous like this. So this should be the actually this should be constant, but since we have the ripple voltage, then we'll have the ripple current over here. So please go through it and try to understand. Although this may not be good, it may not be for your what I want to say. It will not be set in the exam. Okay, so I think that's it from chapter 5 of this one. So we shall go to the three-phase control rectifier. So three-phase control rectifier we have not started, did we? Hello.
No, sir.
What do you say? We did not start, right? Okay, so three-phase control rectifier without LS, we shall see a video. Okay, just wait and let me find out the video. Okay, can you hear me? Oh,
Yes, sir.
okay, can hear. Let me now share the video. This is nothing but the three-phase control rectifier. That means the SCR rectifier without LS. Okay. Okay. So I have also given this link to you in your WhatsApp group today. Is this video is now available to you? I have not played it. Can you see the?
Yes, sir.
Okay.
Back, everybody.
Can you hear the sound? Listen the sound.
Yes, sir.
Okay,
Yes.
now.
This is ELNC 1533. This will be the first in a series of videos, I hope. We're still covering Unit 3 material here. And what I'm going to start with is looking at how to determine the waveforms for a 6-pulse 3-phase rectifier.
Control rectifier.
So behind me, you should be seeing the rectifier and the line-to-line voltage diagram. And then below that, we're going to solve out what the individual currents look like as well. Okay, so starting with line VAB, the first
Is it visible?
Yes, sir.
Okay.
letter tells you which device is going to conduct in the positive half cycle, and the second letter, in this case B, tells you which device on the negative leg is going to return the current to the AC system. So I'm just going to
circle the two devices of interest here. So we've got Q1, which is your phase A positive device, and we're coming back on phase B, so that's Q6.
Same as before.
So those are the two devices that are conducting. When Q1 first becomes forward bias, doesn't happen at the zero cross of the line-to-line voltage VAB, but rather 60 degrees in. So alpha 0, I'm just going to highlight that for you right down here, happens.
So he said that this VAB does not necessarily to go to 0, rather than it has to be the highest value. We shall take the 0 from here. You understand that? From here, sorry. The 0 originally will be from here, and from here to here it will be 60 degrees. Can you see my cursor?
Yes,
So-
sir.
So if you go back, and it is the 0 crossing with the omega t equal to 0 axis, but we shall start where, like here, like
At this
like
point
here,
on
okay. So we shall start from here. It does not necessarily mean that we have to start from here, because our starting point will be from here, and this will be from omega t equal to 0 for VAB. Suppose, say it will start from, so after pi by 6, that after 60 degrees. This is 90 degree, right? Can you see my cursor? This is 90 degree position. This is your 60 degree position. So they are starting from there. Okay.
VAB,
Okay, I'm
which
just
is
little going back. Like
alpha 0, I'm just going to highlight that for you right down here, happens at this point on VAB, which is 60 degrees in on line VAB. But let's say that we gate at 30 degrees. What is that going to look like for a waveform? So let me grab a green highlight here, and I'm going to start up right at this point here. So that's 30 degrees on line VAB. Now I know that each of these devices is going to conduct on a 6-pulse rectifier for 60 degrees, and each one by itself. So looking at Q1, so we're firing Q1, is going to conduct initially for 60 degrees, and then we're going to turn on a different SCR in the negative half leg. So you're going to see another transition at 60 degrees.
what he wants to mean that, so your DQ1 or here T1, whatever.
But
Oh.
each device,
It should conduct from here to here. Okay. This one is nothing but the pi by 3. That means 60 degrees. You got my point? Hello. VAB is the highest voltage here. So if A is conducting, this is from this blue line to this green line, this is 30 degrees. From green line to this point is 30 degrees. So altogether 60 degrees. So each device, say A will be conducting all these 60 degrees. And A is conducting means Q1 will be conducting. Okay.
by itself conducts for 120 degrees. But let's just follow line VAB. So for this moment in time here, we have Q1 and Q6 working together. Okay, but what happens at 60 degrees in at this point, which is now at 90 degrees as far as alpha is concerned? Here we have to fire phase A SCR again, which is Q1 on the positive leg. So we switch up here, and this time current is going to return through Q2. So I'm just going to grab a different color marker to show that on the second part of the conduction, Q1 is still conducting all the time, but on the second part of Q1's conduction, the current commutates off of Q6 and then on to Q2. So if I highlight that, you get this waveform. That represents there the full 120 degree conduction for Q1. So Q1, I'm just going to draw a line here. So Q1 is conducting in this period of time right here.
Why Q1 will be conducting D? Because look here, A, BAB and BAC. A is there. So as long as A is there, so your Q1 has to be conducted.
And if you look at Q6 was on in this period of time, and
AB.
presumably before that as well. So then the rest of the time, Q2 is going to pick it up.
Because
So
it is C.
Q2 is going to be in here. And if you look at the next part or the next line-to-line voltage that's going to be conducting, you see the letter C in the second case out to here as well. So having drawn 120 degrees of conduction waveform for Q1, we can assume, as long as you haven't changed the firing angle, that the waveform is going to continue along that pattern for the rest of the cycle. So the rest of the cycle then is going to look like this. And let me just make a note of the fact that this is with alpha equal to 30 degrees.
This is
So that's
very
the
important. Look here. So they have paired that Q1 at alpha equal to 30 degree. And then when it is turned on, that will be continuing from here, 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 as long as A is concerned, phase A is concerned.
resulting DC waveform you're going to get with alpha equals 30 degrees. I'm also going to draw what the currents would look like down in the bottom. So if we look at Q1, yeah, I'll stick with blue. So if we're looking at Q1, Q1 turned on right here. And it stays on until this point here. So SCR Q1 is conducting in there. And you may get a test question like this. So the thing is, you look for wherever the first letter is on the waveform. Once you've got the timing in place, the first letter tells you which device is conducting the positive half cycle. The second letter tells you which device is conducting in the negative half cycle. So I know that I'm going to be off now for at least 240 degrees. So you're on for 4 divisions, and each division is 30 degrees. So this is going to be off here, then it's going to be off here, and then it's going to come on again there. Now what about Q2? Q2 is the return path in the second half. So we know that Q2 was going to be picking up the ball here and put it on for 2 more cycles. So it's going to look like this. And then it's going to be off for 4 divisions. So we wouldn't see it coming in anymore within the time constraint of this chart. Q3 is the next one to pick up the ball after Q1. So it's going to look like this.
That's up to 60 degrees.
And be off the rest of the time there.
And duration will
Carry
be
on like
150
that.
degrees.
I'm going to jump down to Q5 because that one's easier for me. So Q5 will pick up the ball after Q3, which is the phase CS here. And move over a bit. I know it would be on at this point here as well. So that draws that one out. Okay, so coming back to Q4. Q4 is phase A. So what I'm looking for in the waveforms is where the letter A becomes the second letter. And that happens right at this point here. So I come down, so I know it's going to be on there. And it's going to be on for 120 degrees again. So I can draw it out like that. And it'll be off for 4 in front, and it'll be off for another 4 before that. So we don't see it anymore within this picture. And now I come to Q6. So we know that Q6 was on at this point for phase A. So it was on here. And then it'll be off for 4 more. So that's 1, 2, 1 more. And then it'll be on the rest of this time here. Now, if you're wondering, why do we sequence the labeling here in this picture? So if you look at the schematic, you'll see that the top 3 SCRs are Q1, Q3, Q5, and then the bottom devices, Q4, Q6, Q2. And it seems like kind of a weird sequence, but look at our timing chart. So I've put them in order of Q1, Q2, Q3, and so forth. But if you look at the waveforms, you can see them all moving in the same direction. So that shows you that the actual sequence in which those devices commutate from one to the next actually occurs in the numbering order. So even though it seems a little bit random in the schematic, the number actually represents the sequence of turn on. Okay, so those are the devices for a 30-degree angle. If you're firing at a different angle, you're just sort of shifting all that stuff around. But what about phase A? What does the actual line current look like on phase A? So I'm just going to go to a different color here so we can show that line current. Now let's go with red. All right, so Q1 and Q4 are both connected to phase A. So Q1 represents the positive half cycles. So what I do is I pull down Q1's waveform. And this is what the current's going to look like on the AC line for the positive half cycle. And now I got to find its negative match. So when current flows the other way through phase A, it's going to come back on Q4. So looking at Q4, that I'm going to draw now as a negative current because that means it's going the opposite direction in line A from what the current was when it was going through Q1. Okay, so the red line now represents what the AC line current is going to look like. And I should note for you that the current going through the DC here is basically flat. So if you look at the current ID as a function of time,
Constant
and
current.
you basically have a flat current. And so what we're assuming is that the inductance is large enough to filter out the AC ripple. And you guys should know at this point in time that if you look at this waveform, we have 1, 2, 3, 4, 5, 6 symmetric pulses that are happening in each cycle. So the AC ripple frequency across the DC load is actually 6 times 60 hertz or 360 hertz. So the fundamental ripple frequency again is 360 hertz at the load, even though the AC line frequency is 60 hertz. Okay, let's
You understand what he's saying? It is very important. He said that the input line frequency, voltage frequency is 60 hertz, but since you are getting the 6 pulses, so your output voltage frequency will be 6 multiplied by 6, that means 360 hertz. So, so you are getting more DC.
switch it up a bit and let's look at some different angles. So I'm going to take the same thing and I'm going to just erase everything I've done here. All right, let me pull up my green marker again. Well, just a second, guys. I got a dog in here.
Dog.
Go on. Okay, here's my green marker. Last time we looked at 30 degrees. Let's look at 60 degrees.
60.
So I pick off 60-degree point on VAB. I know I'm going to go for 60 more degrees before I fire the next pair. Still using Q1 on the positive. So basically, what I've just highlighted for you right now, that's with Q1 being the positive feed. Halfway through, it comes back on phase.
Can anyone tell me why the voltage it is not going like this rather than it is going here? Because the next device will be fired after 60 degrees, so it will continue to conduct until the next device is fired. Okay.
B, and then on the second half of that time it comes back on phase C. So just to show you, so for the first part, current's coming around this way, coming
Because
back
this
on
is
phase
still
B.
A, right?
That's the
A.
first part. Let me
So,
change the
Q1.
highlight color, and then I can show you what the path. So for this second part right here, the current is still going to come through Q1, but this time it's going to come back on Q2. Okay,
AC,
so
AC.
for both parts of that, we're using Q1, but 60 degrees in,
Since
the
it is
ball
following the
transfers
AC,
over from
BAC.
Q6 onto Q2. And that you can work out based on the current waveforms we had before for each of the other devices as well. All right, so let me carry on with the rest of the waveforms. So for 60 degrees, your waveform is going to look like that. Now, what does the average DC voltage do? Well, the average sort of comes down the middle of that. So your average DC voltage is going to be sitting in around there somewhere, probably a little bit lower than that. So this is your VDC. And if you look in the WildE textbook, you're going to see that the formula for that is
ELL cosine of
1.35
alpha.
times the V line to line voltage times the cosine of your firing angle.
Since alpha is increasing, so VDC will be decreasing.
And we're going to do some work problems using that formula a little bit later on. So anyways, that represents the case for 60 degrees, right? Okay, we've done 30 degrees, 60 degrees. How about, well, let's look at the special case of 90 degrees. So again, coming down to 90 degrees, I end up with a waveform like this, goes 60 degrees, switch up, and I just keep painting that pattern all the way through. And this time, you notice something. Your average is a line right down the middle. So basically, you
Cosine
have as
90
much
degree
time
equal to
above
0, right?
the zero axis.
Yes,
Hello,
sir.
you understand? Root 3, sorry, 1.35 ELL cosine of alpha. So alpha equal to 90, of course, the average value must be 0. You understand it? So look here, my cursor. So he has started the fire, they have fired the alpha equal to 90 degrees. So it will continue like this for this phase, this phase, this phase, this phase, this phase, this is the previous phase. And then it will go to the AB, and that AB will continue until the next devices are fired. Then it will go like this and this. So if alpha equal to 90 degree, you will get
As you have below the zero axis. So the net result at 90 degree firing angle is you have a 0 voltage overall. So you're never going to get any current going through, say, an inductive field at 90 degrees because you've got as much voltage above the 0 as you have below it, and they just cancel out over the cycle. You can see that from the formula too, because if your DC voltage is equal to 1.35 times V line to line times the cos of 90 degrees, well, the cos of 90 is 0, so it doesn't matter what your line to line voltage is, you're just going to end up with a net 0 voltage. Now what happens when we go past 90? So now let's pick off 120. So follow my VAB all the way down to 120 and then continue on that line to line voltage and just keep painting that off like that. You can backtrack that.
it will be
and
opposite
that's
of
your
cosine
waveform.
alpha
So the
equal to
entire
30
time you're
right?
firing at 120 degrees, your average voltage is now less than 0. In other words, it's negative. So how can I have a negative voltage? Well, if you have a highly inductive load like I'm showing here in this picture, at some point in time, let's say your current's coming around like this, and we'll just say that at this moment in time it's coming back on phase B. SCRs have to be forward biased to keep conducting. So obviously the polarity on the SCRs is going to be like that, otherwise they would be shutting off. If current is going in this direction, then you would have to have positive and negative across your resistor to respond in that way to the current, right?
What he wants to say that the value, the voltage drop across the resistance and also across the inductance, if you add it, then this voltage, the voltage across the inductance will be more negative than your resistive voltage, then you will get the negative voltage. So we don't need to go through all these things.
Resistors are just pure loads, which
So
don't.
yes, said
Sorry,
how-
I'm doing this wrong. I'm played to by
he
the
has
inductor. So
explained all this.
the energy is the only thing that's keeping. So irrespective of whatever the AC voltage is at that moment, the inductive
he has
volt
explained
drop
how
is negative
the negative
enough to
voltage
keep
is
the net
Yeah, we don't need that. Okay, so although it seems to be little difficult, but if you go through the video several times, then you will find that it is not that much difficult. Okay, so that is the without ls. So you should go through the video and then you can also go through your book. So should I start the circuit with control rectifier with ls, or we should finish today?
Next class, maybe, sir.
Next class, right? Next class, then we have to. Okay. Where is my book? This is my book. Okay. So, this is your chapter 6, right? Chapter 6, we have already covered all these things now here. So, in the video has demonstrated the same thing here, and that has been like here omega t equal to 0. Then they have just applied the firing pass here, so this voltage will continue, and then when this will be fired at omega t equal to alpha, then this voltage will continue, and then again when this one will be fired, then this voltage will continue. With this one, they have shown you the phase current he has shown. That was easier for you, because that will be your 120-degree conduction, 120-degree conduction, and for your line-to-line voltage, that is this one, and this is this one. But if there is no ELS, we will get that. Okay, because of the because of the alpha. So if there is no alpha equal to 0, so we will not lose this voltage. It will look like this. Okay, this A alpha will be deducted from your say 1.35 VALL. Then ultimately, if you do all this calculation, then the VD alpha, that means it will come as VD0 cosine alpha, where VD0 is nothing but 1.35 VLL. So that has been already demonstrated in your video. Okay. So, and then if the input current wave shape will be like this. Can you see my cursor? Hello. Hello.
Yes, sir.
Hello. This current is not sinusoidal, so it will continue a lot of harmonics. So if you do the Fourier series, then they have demonstrated this one, and then there will not be any even harmonics, because that is symmetric with your x-axis. So only the third harmonics, fifth harmonics, all these things will be here. No, third harmonics will be also because this is a three-phase line, and you know that three-phase third harmonics will eventually go to 0 from the power system concept. And then from there you can find out the what is this one? This one will be the fundamental component. Previously it was IS1 and 0.9 ID. Now for the three phase it will be 0.78 ID. And so for alpha equal to 0 degree, for alpha equal to 30 degree, for alpha equal to 60 degree, alpha equal to 90 degree, alpha equal to 120 degree, whatever in the video they have mentioned that has been demonstrated here. And that is your VAN, this is your VBN, and this is your VCL. This is your VAN, and what is this? This is your VCN, this is your VAN. So with respect to this voltage, they have also plotted the current. With that one, they have shown total harmonic distortion, that will be your IS1 by IS, that will be 0.955, and total, sorry, that will be IS1 by IS equal to 0.955, and the total harmonic distortion, you know the formula, IS1 is star minus IS star minus ISS divided by IS1. If you put that, then you will get 31.0. So you see that the total harmonic distortion is being reduced. Displacement power factor will be cosine alpha as previous, and power factor will be now 3 by pi cosine of alpha from this one. So will not describe all those things. And now the effect of the ALS. This is very critical now. We'll have to again go through this as what I have done. For the diode case, we'll have to consider this one. Look here, same thing. What we have to consider after alpha, there will be a commutation delay. We'll have to find AU. That AU will use the same concept, and then we'll find out the AU that will be same as omega less ID, and then VD will be, this will be your 1.355 ln cosine alpha, and that will be the voltage which we have to lost. And then from there, the same procedure what we have done for your what is that, for your diode rectifier, we shall of course will find out the expression of the commutation. That will be, and then with that one, the IS will be the same as diode rectifier, half U, and the displacement power factor will be this one. Up to this, that will be the your main things, and then we have from the AC to DC converter, and probably in the middle of the next class, or maybe the class after the next class, we shall start the DC-DC converter. How many classes are left? Hello. Hello.
Sir,
Hello.
around 4 or 5, I think. I'm not sure, sir.
So, yeah, so 4 classes will be left, and we shall cover all this thing DC-DC converter by 3 classes, and 4th class will be for your inverter. This inverter will be covered by your from your Haruna Roshi books. Okay, whatever you have already done for your undergraduate, that will be repeated. Okay, so that's the end of today's class then. So how many of you present today? 19. So 4 students are absent. I don't know who are those. Anyway, so then I'm ending the session. Okay. So, but the best thing is that before coming to the class, next class, you should, from the book, you should try to understand the concept of the LS for your conflict rectifier. Okay. Can I leave?
Okay,
Yes,
sir.
sir. Okay, sir.
Assalamu alaikum, sir.
Welcome.